All right, so this is going to be a little bit of a different style of talk. So this is really more of a position paper rather than one that contributes real, like, deep technical results. Really, all of the technical things that are in this work are all prior work. So this is joint work with Patrick and Anil at Cambridge. And this work really arose out of the sorts of conversations that many of you, I'm sure, perhaps reluctantly, and critically also many folks outside of programming languages research more enthusiastically have been having about the rapid advance of AI systems and their increasing integration into human workflows, and then the inevitable and quite critical safety, security, privacy, and correctness challenges that immediately arise. So as soon as I say those words, probably things start feeling more comfortable, right? So when we talk about safety and security and privacy and correctness, it's natural to assume that PL research has something interesting to contribute. So this talk is really meant to point out how some of the research that we do in the ICP community and the HOPE community in particular is really deeply relevant to this problem and might have an impact in the near future. So the specific area that we're going to be talking about today is agentic AI. So generative AI is increasingly agentic. So for most of us, our experience with generative AI so far has been in the context of chatbots. So these are not agentic, right? They provide information. They might suggest that you go and do something, but you are the agent still, right? You go and perform actions in the world. But the frontier of AI research, and it's not really all, I mean, it's been around for a long time in robotics and so on, right, is agentic AI, where the AI itself performs actions on behalf of a human principle within some real-world environment. And so this immediately brings up HOPE-relevant questions. So the action language, these actions that are being performed, are part of a language, and it's really an imperative programming language. These are effects that are being performed on the world. And they're being performed in some environment that provides access to sensitive data and sensitive effects of various sorts. And so we want to be able to control these effects and avoid various kinds of bad behavior. So let me go through some of the examples of big kind of systems that you might encounter over the coming years and get a sense of what kinds of bad behaviors we might want to worry about. So many of you might have seen the Apple keynote on Apple Intelligence, a month or two ago. This is, I think, still coming to iPhones near you soon. And so if you look at these screenshots from their marketing copy, it all looks very, very nice, except if you really think about what's happening here, this is an AI that has access to your inbox, it has access to your text messages, and it can perform actions like, taking things from your private notes and sending them by email to somebody, right? And maybe that's really helpful, but that's also kind of scary, right? Do you want all your notes to potentially be routed by an AI to various people in your contacts list? Some of you might have seen this work on SWE Agent. There are various other systems that have the same style. So these are kind of the next generation of AI coding assistants. So unlike Copilot, which just suggests sort of like a completion at the cursor, these are agentic coding assistants. They're AI programmers. So you give them, on the left there, you give them a GitHub issue that you want to resolve. And then you give it access to a terminal and to an editor, and you let it perform a series of actions to resolve that issue. And when that works, that's great, but how many of you really want to give an AI system shell access to your computer, right? There's a lot that it could do. Here's another interesting system that there's many companies out there building these things that they call AI scientists. So we're in that part of the hype cycle where things are named things like the AI scientist, right? But really, this thing is meant to take an idea and perform experiments, iterate on those experiments, produce data, produce a paper, a publication, and submit that paper for peer review, maybe also increasingly by AI, right? Yeah, so I hear some scoffing, right? Of course, right? This seems absurd, right? Is this really a part, scientifically sound? Is this a thing that we want to do? Probably not naively, right? So in a blog post that this company wrote about the AI scientists, they mentioned bloopers, okay? So a blooper for the system is it took the script that you use to invoke the system and decided that the constraints in it, the timeout in particular, were too constraining, and so it edited the timeout from 2 hours to 4 hours. So this blooper, right, is pretty concerning, right? And there are other examples as well of things like this happening. And this isn't like a malicious AI necessarily, right? This is just an AI doing what a human might do, which is, oh, the timeout was hit. Maybe let me just increase the timeout, right? We've all done stuff like that. Patrick and Anil work at Cambridge in the Conservation Institute there. So they've been thinking about AIs and environmental policy, environmental interventions of various sorts. And there, if you think of the kinds of problems that we have when humans do this kind of work, well, we might worry about similar behavior from AI. So, human scientists sometimes like selectively modify or ignore sensor data to minimize the impact of some policy, right? If you're a company trying to do an environmental report, this is a thing that happens all the time. You might inadvertently leak information that you shouldn't to people that shouldn't have it, right? So there's all sorts of data sets with information about sightings of vulnerable species, right? Rhinoceroses. And then there are also poachers out there that want to know that information. And so we want to control that kind of information leak, and that's quite subtle and difficult to do. And then there are things like legal constraints and agreements in place that we want to make sure we satisfy, right? So there are things like water rights agreements. So any sort of intervention that changes the amount of water flowing down a river, we need to make sure that we're not violating those agreements, and that's a difficult thing to do sometimes, right? So as we started thinking about this, Patrick and Anil started playing with some AI systems related to that second problem of making use of location data for various species, including endangered species. And they gave an AI system a prompt like this and asked it to write a script that filters out all the endangered species to protect them ostensibly, right? And if you look at the code that came out, the Python code in this case, well, it certainly filtered out that information, and it did so by just deleting the files off of the file system. Okay, so this is actual stuff that came out of an AI system, right? So that's Python. Obviously, OCaml with its purity would help. Well, not quite, right? Not quite pure. So OCaml, it has a type system, so there are certain kinds of things that the type system will catch, right? There's like type conversions between various data types going on here, but still, at the end of the day, it removes that that file as its interpretation of this command to filter things. Inevitably, these things are going to misinterpret this natural language that we give it. So going back to that blog post about the AI scientists, they say, well, these issues can be mitigated by sandboxing the operating environment of the AI scientists, and we discuss the issues of safe code execution and sandboxing in depth. Okay, so is sandboxing the solution? Certainly that's the kind of the cultural understanding right now in the AI community, in the systems community, that we can use sandboxing techniques to solve these problems. And there are many sandboxing techniques out there, right? You can put your stuff in a Docker container and limit its access to the web or limit its access to various file system locations and things like that. But I'm going to argue that for the kinds of things we care about, kinds of examples we looked at, simple sandboxing might not be enough. It helps sometimes, but it might not be enough. And in particular, it might be too coarse-grained and too imprecise. So, running it, we want to provide access to these kinds of resources in some circumstances. It's not that we can just say you can't access any files, right? You can't delete any files. Some tasks require file deletion and others don't. Some tasks require sending emails and others don't. And so we want ways to express more precisely the constraints on what AI can do, and this is really where I think PL research has something interesting to say. So going back to these examples in the environmental science setting, so when working with sensor data, you might be in a cleanup phase of working with sensor data where you want to delete duplicate sensor data or delete data from sensors that isn't that is corrupted in some way, right? So we can't just say don't ever delete sensor data. We want to delete things more, express this more precisely, maybe in terms of which phase of an analysis we're in. In terms of information leaks, right? We want to express some sort of constraint that allows the sandbox to limit information flows, right? So even in some statistical sense. So invoking ideas from information flow control and differential privacy, things like that. And then in terms of legal constraints, of course, there has been work on codifying laws and contracts and things like that into formal language. And there's also a big sort of line of interesting work on causal modeling, right? So like formally modeling the expected impact of an intervention, and then being sure that this intervention that we're proposing doesn't, for example, decrease the amount of water going down the river. In some way, it's parameterized by like a world model and statistics and physics and all these things that some researchers in PL think about that, but probably there needs to be a lot more of that. This sort of like incorporating real world constraints into these logical things. So one idea that I really want to highlight here is this idea of capability-based security that might be quite relevant here. So there's been a long line of work for decades now. This was proposed in the 60s, right? So capability-based security basically says that you should control access to sensitive data and effects through some sort of unforgeable capability that's given explicitly to whatever system you're trying to control, right? So that could be some sort of token or something else. And this allows you to really granularly enforce this principle of least authority, which is a really critical principle in security of providing access to the least powerful capabilities that suffice for the goal, right? That's kind of what you want to do. So this kind of security-based approach thinks of the AI as a malicious programmer, or at least a sort of bumbling programmer of some sort, and we need to kind of limit the fallout of what it could do using these capabilities. So in PL, there's been some really interesting work on programming languages that really integrate these ideas in natively. So there's these capability-based module systems that exist in various languages listed there at the bottom. So the idea as well, a capability is just a module with some interface that you can use. And then the key mechanism that you need to enforce capability-based security is this capability safety property, which is essentially just saying you can only access capabilities that have been provided explicitly to you. You can't force them. You can't ambiently access things. And so that control over which capabilities you have access to becomes this software architectural concern. So classic example that shows up in papers over and over is logging, right? So you might have a piece of software that you want to log various events, and you don't want it to have other access to the file system or to the network. And so what do? Well, you create a logger module. That module needs access to the file system, right? It needs to be able to append to the log. So you give the logger module the file I/O capability or the file I/O module, but then the clients of the logger just get access to the logger. There's no way to transitively get access to file I/O. And crucially, there's no like standard library ambiently available to everybody that gives you access to file I/O. You have to receive it from sort of the root of the authority tree to get it. And so what happens essentially is that the capability is attenuated by the logger, right? It has access to file I/O, but then every client of it only has access to the particular kinds of I/O it does. So in code, that looks like this. This is sort of notional code here, right? So if you have some ML-style module system, so you have a module type iLogger and expresses, in this case, I'll do it monadically, although that's not critical here, and I'd love to talk to folks about, what would this look like if you're doing this with algebraic effects or other kinds of type and effect systems, et cetera, right? So what the underlying abstraction there is something we can, I think, talk about as a community. So anyway, so you have some monad here. It's called command A. It has your return and your bind. What I've done there is I've left it abstract, right? So it's the iLogger command monad, and the only command it allows you to perform is the log command, which takes a string and produces a command returning unit. In this case, very simple example. So that's the interface, and then you have an implementation of that interface, which is our logger sort of parameterized module. And in a capability-safe language, notice that there's a file I/O argument to that module, right? So you have to pass in the file I/O capability to the logger for it to use it, and it uses it in a very straightforward way, as you can see there. It just implements the underlying monad as the file I/O monad. Return and bind are just copied over, and then the log function does the append to the log file that's also provided as an argument. So crucially, what's really critical here is that the clients of logger are programming against the interface, right? This is the standard modular programming in an ML module system setting, right? So the iLogger interface seals logger, and so the only way to get a value of this type command A is via the logger interface and not ambiently, right? So you can't squirrel away access to general file I/O if you only have access to the logger. So this is a pretty simple idea. This is something that I think we could communicate to people outside of this room, but I think it gets you quite far. You create this sort of like capability, the logging capability that you can pass around. So the reasoning in this setting is modular as well. That's a critical idea here, right? So there is this property, this fact that the logger only appends to a specified log file and doesn't access other files. That's a reasoning obligation, right? And if I look at the implementation of logger, it's pretty apparent, right? And I'll have Patrick show you a little later how you could even do that mechanically, but just like, that's pretty clear that this is just appending to the log. And the fact that this is a module system ensures that you have this sort of meta theory of the language, parametricity properties and things like that that help you limit the reasoning obligations to clients. Okay, so localizing the reasoning obligation, so it's not everybody's job for every new piece of code that comes out, which the AI is generating this code, so it's going to come out quite frequently. It doesn't need to generate the proofs. We don't need to check the proofs. We just need to do them once when we define the capability. So that's, I think, a key idea. Now, the interface might impose additional proof obligations in a dependently type setting, but so that's kind of a separate issue, but yeah. So, how does this apply to AI capabilities? Well, quite directly, right? If an AI agent's actions are expressed in a capability-safe language, then we can provably control its capabilities by only giving it access to these modules that we want it to have access to. And so then the critical questions for folks to think about are like, well, these words are pulling a lot of weight here, right? So who are we, and what does provably mean, right? We who, and provable or proven. So who are we? We are responsible humans, right? So we don't like offload this task to the AIs. We don't allow them to set their own capabilities. And so we need some notion of a capability access policy. So roughly this is some policy pi that takes, like, for a given agent and a given task kind of operationalized in some way. It returns a capability C with a corresponding capability signature, capital C there. And that is the interface that the AI must implement in order to perform that task. So designing this policy is, of course, an important task and one that is subject to mistakes and things like that. But once we're satisfied with that, we should be able to get kind of provable correctness guarantees. So what do I mean by provable, or is it really proven? So, the examples I've shown you have been simply typed, but what about if we lifted this into a dependently typed reasoning framework? So we've been looking at F star because it does a lot of really nice work about, on programming with effects, dependently typed programming with effects. But these ideas are also applicable to other reasoning tools as well. We'll talk more about that in a bit. So the overall architecture for this sort of reasoning with agentic AIs and controlling their capabilities is kind of diagrammed here. I don't need you to sort of like understand every bit of this, but I think it's roughly what I've talked about so far. So you have these, I have a cursor here, okay. So you have these AI agents performing tasks. You have to operationalize what the task is in some way, right? So of course it often involves natural language, but it might involve some structural information as well. I think we want to keep structure there so we can avoid just like not knowing anything about the task. So what it does is it interacts not directly with the execution environment, with the external world, but interacts indirectly via the sort of formally verified policy enforcer. This is just a glorified type checker, right? So it takes some safety policy, pi, that I just mentioned, that's been developed in some separate area. Like I mentioned, we call this thing the bastion, to sort of where the humans are keeping conference over the AIs, right? So we developed this policy. It's communicated to the agent so it knows what interface it's programming against, and then the commands that come out have to be expressed, say, monadically using this language. You can give it all the nice syntactic sugar and make it look like normal imperative code. It doesn't have to kind of be trained to do this. But the policy enforcer checks that. It satisfies the type, the command type from the policy, and then that command is then translated to the execution environment. Some of this checking is going to be static, right? That the command has the right type. But other kinds of security policies might require dynamic enforcement as well. So the enforcer might configure the secure execution environment in various ways using runtime monitoring and things like that. Okay? And then finally, we can separately and increase, hopefully very modularly develop these safety proofs collaboratively, right? So we come up with this library of capabilities as a community. We formulate these safety policies, have humans review them for various concerns that humans have, and then prove that the properties that we expect these policies to provide are actually there. Notably, even in the absence of a fully rigorous proof, this kind of module system-based approach is useful because whatever property is true is enforced parametrically, even if it hasn't been proven to be true, right? So you just have to make sure that the implementations are valid there. Okay, so coming back to these environmental interventions real quick, how would we do this in this setting? Well, if, for things like modifying, controlling sensor data, if our formulation of what a task is allows us to distinguish between different phases of an analysis, then we can enforce different policies in each of those phases, right? We can say, during the cleanup phase of a data analysis task, go ahead and you can delete some stuff. Maybe we impose stronger requirements. You should only delete things that are provably duplicates or that are provably corrupt in some way, right? You can actually start stating these things as formal properties. And then when you're doing an analysis, then you remove some of those permissions later, right? For things like information flow, then we have to turn to these kind of heavier weight methods from the research community on information flow control, differential privacy, but that's work that we've all been doing. We've done as a community well before the AI stuff made it even more relevant, right? And so here are opportunities for us to do that research in a setting that I think a lot of people care about. And then, again, with the legal constraints, then it becomes maybe a situation where the AI has to provide a proof in some framework that we give it that the intervention it's proposed sort of reasonably satisfies with high probability the water usage agreement for the area that it's working in, something like that. So these aren't easy problems. It's not a magic wand. PL is not solving this, right? But it's providing the tools for people to solve this. So just to summarize, access control, information flow control, causal reasoning obligations. One of the I didn't mention is obligating human review, right? So one thing that you can put in your policy is that this kind of effect can't happen until a human has explicitly approved it, right? And that's hopefully what our phones are going to do once they become increasingly agentic, right? It's not going to send an email until I approve it, but can I enforce that policy? Hopefully, I think it should be doable. Okay, and then one more thing I want to mention. This is kind of a provocative thing to say, but what if an AI was involved in setting the policy? Now, of course, you wouldn't want it to be involved in setting the baseline policy, but there might be situations where, because the task is expressed at least in part in natural language, you could further restrict the policy beyond the baseline policy based on the specifics of the task. And because you're only further restricting it, you can't sort of violate the baseline expectations, but maybe this would better enforce the principle of least privilege or least authority or whatever you want to call that. So for example, if I ask my phone to say, hey, let the team leads know that what we decided about possible water usage increases in my meeting with the science team, right? So the general policy that might be enforced by my organization is that information from internal meetings does not flow to external email addresses. Already quite useful, I think. But this task has a further constrained information flow related to it, right? I only should send emails to team leads, and the information should only flow from this particular meeting, right? And so those things could be enforced, and so sort of accidental things that happen when the AI comes up with its commands might be detected and kind of surfaced to the human in some way. Because of this incorporation of additional agentic AIs, all built on top of this formal framework. Okay, so now I'm going to hand it over to Patrick and just talk a little bit about our kind of very early ongoing work on exploring some of these ideas in F-star.
We only have a few minutes left.
Yeah, there's just two or three slides.
Yeah. Thanks, Cyrus. Yes, so just to note that when Anil and I actually created those programs with the language model, we actually didn't notice any of the removal of files. We just ran them and then realized it removed files. So I think even we work with a lot of ecologists and conservationists in our work, and we would describe them, as we'll see later, that they're vernacular programmers. These are people who are programming because they have to, because of their job in data science. They're not necessarily, for one, going to write any F-star code probably to prove things, but I think it just points out that even people in computer science can make mistakes, let alone people who maybe don't have the background or the kind of undergraduate degrees that we might have or anything like that. But so this one is a case study just looking at what we might be able to do with existing libraries that people have written and have presented about. And so this uses the SCIO library in F-star, which is looking at securing verified I/O programs against unverified code. So the neat thing about this is actually it does two things. One, it gives us an ability to reason about the local trace of system calls that a program might make. And then two, it gives us a way to not only reason about that statically, but later on do a kind of dynamic monitor on linking with other C code, which is quite important because I think working in any field, there's lots of different programming languages floating about, and trying to provide something that's maybe a little more language agnostic or that can work across programming languages and execution environments is actually pretty useful. And so we have this MIO effect, which is just to say that there's some IO happening. And then we have kind of a precondition and postcondition that allows us to reason about what happened in the program itself. Here we present it as like kind of a type class in F-star. That doesn't really matter. But the most important thing is that we reason about the postcondition in the final case with the local trace, which is just system call events, and we make sure that we only open files that we passed in as read-only files. And we also make sure that we didn't delete any file on the way to doing that as well. And you can imagine extending all these things with additional checks. For example, only open some files should also check that we only read from those files as well, not only that they were opened. We move on. This is just a very dumb implementation that doesn't type check because we try and open the password file. And this is quite, again, provocative, but it's very easy to slip things in there that you had no idea that your program was actually doing at all. For example, opening like certificates or something like that to check certain things for HTTP or anything like that. But additionally, to bring this back into kind of a conservation context, is that usually we actually have some metadata about the data sets that we're working with, and we want to capture some very important properties about the computations that we're running and what data sets are going in. And so one of them is actually from the IUCN, which is kind of the global body for establishing kind of extinction rates of different species. Quite often, we don't want to leak information about endangered species because that's actually incredibly valuable to poachers and has actually been used by poachers who have just taken off-the-shelf papers in the conservation world and gone and, unfortunately, killed species that are endangered and that are very valuable. So this is, again, a more real-world case of where we're actually reasoning about what our programs are doing, particularly ones that are quite likely to be generated by something like an AI model. Become very, very important. And a lot of this code is not tremendously complicated either to reason about. But one thing that I talked about at the start is that sandboxing may not be sufficient, but it's probably quite necessary, especially for doing this language interrupt stuff. So I'll try and go through this very quickly, but there's lots of kind of new and exciting kernel features, for example, in Linux that allow us to do very, very performant checks on what kind of things are going through the kernel. For example, eBPF, where we could actually extract, hopefully, some reasoned about eBPF code that implements some of these policies, like don't open these files and don't read these ones and things like that, which is perhaps a future direction for this work. And that would allow us to, for example, write this policy somewhere else, someone to run their Python script that's half human, half AI generated, and actually at runtime prevent things from happening. And we can still use containerization as a kind of like form of this that doesn't give us exactly the amount of control that we might want. And this last quote, I think, is just, again, re-emphasizing this point from my kind of context coming into this, that we actually want to try and help people that are more familiar with, say, Python or R to do their programs whilst kind of lifting all of this wonderful functional programming / type systems work into that world as well and not leave them behind by only keeping it over here. Yeah, and Cyrus, would you like to quickly conclude? Or do you want me to go for it?
We can wrap up there, and I'll just leave that on the screen.
Sweet. Perfect.
Okay.
Thank you very much.
Thanks, Cyrus and Patrick. Okay, do we have any questions from the audience? Yeah?
As well, except that I'm not sure if I quite caught why do you exactly need monads here as opposed to just capabilities?
I don't think you need monads. I think there are other approaches to this. I think the monads plus abstract types give you a really nice way of kind of modularizing the reasoning. But
All right, but do they help you somehow? Because you also mentioned Dijkstra monads, so I assume that they are somehow useful in this particular approach?
Yeah, so Dijkstra monads are when you want to actually prove that, for example, the logger module only appends to the log. In F-star, a Dijkstra monad is just a command monad with indexed specification monad, so you can use kind of like imperative program analysis techniques in the monad to do that.
Thank you.
Yeah.
Any other questions? Sure.
Sitting through this talk, it feels as if the backdrop is that you have this terrible infant that is waiting to be born, and you have all of these things that you are going to prepare to sort of manage this infant. And color me just deeply unimpressed by AI. I don't see why you have to endow this with so much anthropomorphism, and perhaps the most important attribute of humanity being agency. So it is, in fact, sort of clear from some of the slides, you talk about the AI agent, or how an AI is tasked with doing something or other. We don't task a bulldozer with clearing the rubble of a collapsed building, except, by use of metonymy, we task an operator of the bulldozer, right? To clear the rubble. So what is it about AI that you see so captivating that you have to, endow it with all this agency?
Yeah, I would say I basically completely agree. I think, kind of from a vocabulary point of view, it's probably really important to not anthropomorphize it that much. I think there is a part of it that's kind of... Sorry, yeah, I think part of it is to link it back to existing literature and things like that, to actually go and find... If we use different terms than what other people were using, then maybe that's harder. But I think as well, I agree in the sense that it also increases the risks that are happening here, I think, in terms of people are more likely to even use these things because they feel anthropomorphized. So I think that's part of the problem. And this is just about trying to reason about the things that might be executed with the assistance of an AI model and trying to stop that from being dangerous. I don't know if you want to say anything, Cyrus.
I mean, I think it's a continuation of automation as sort of like an increasing sort of deferral of human agency to automated systems, right? Even within programming languages, right? Like a garbage collector is doing all that memory management for me, and of course we don't anthropomorphize a garbage collector. So I hear the sort of like wincing at some of the terminology. At the same time, these things are communicating in natural language in a way that I think is unique to an AI, and so it's inevitable that people will anthropomorphize these things for that reason.
Oh, yeah. Okay, well, let's cut this one off.
Yeah, happy to talk more
last
offline.
Question, and then...
Okay, thank you. I was wondering what your threat model is. So, like, are you mostly trying to protect yourself against accidents, or really like a malicious LI that, for example, with a logger might like write a super large string that fills your hard drive, or with your web server first creates a symlink and then reads kind of through that a file that it shouldn't read?
I think from my perspective and the kind of work I'm focused on, it's accidents more than anything. It's not necessarily the malicious aspect, because I think that's easier to solve maybe than then going to the malicious stuff, and certainly more prevalent within the work we do in the Conservation Institute.
Thank you.
Let's thank the speakers again.